Something entered our solar system last year that, by the rules science has relied on for decades, shouldn't exist. And a new study out of China has just confirmed exactly what makes it so unsettling. This isn't a theory or a speculation. It's a measurement published in Nature in June 2026, showing that this object formed somewhere so cold, so old, and so unlike anything in our solar system that researchers are genuinely struggling to fit it into the framework they've built their careers on. The water inside this comet holds 30 times more heavy hydrogen than anything ever found before. Its carbon ratios don't line up with our solar system. They don't line up with nearby star-forming regions either. They don't match anything at all. And when scientists worked backward from those figures to determine when and where the object was born, they arrived at an age of 10 to 12 billion years. The universe itself is only 13.8 billion years old. This thing has been drifting through interstellar space for longer than our sun has existed, and it just swept through our neighborhood. Read that again if you need to. This is the story of 3I Atlas. What it is, what China discovered that nearly slipped past the rest of the world, what the newest science says about its origins, and what it all means for everything we thought we understood about the cosmos and our place in it. July 1st, 2025. The Atlas Survey Telescope in Rio Hurtado, Chile, picks up a faint object moving across its nightly scan. Its automated system flags it the way it flags thousands of objects every month. But this one stands out. The orbital math comes back wrong. Then it comes back wrong again. The numbers aren't a mistake. The object's orbital eccentricity around the sun measures 6.14. An eccentricity of 1.0 marks the line between an orbit that's gravitationally bound and one that's escaping entirely. A reading of 614 doesn't describe a comet drifting in from our system's outer edge, and it isn't a long-period comet swinging back after millions of years. It describes something moving so fast, on such an extreme path, that it could only have arrived from another star system altogether. Astronomers named it 3I's Atlas, the 3I, marking it as the third confirmed interstellar object. The first was 1I Oumuamua, spotted in 2017, an odd, elongated body that shot through without a tail or any of the outgassing typical of comets, leaving scientists puzzled before it vanished again into the darkness. The second, 2I Borisov in 2019, behaved more like a comet scientists already understood. 3I Atlas was unlike either of them from the start. Its eccentricity was far more extreme than both predecessors, and its speed relative to the sun, known as excess velocity, was roughly 58 kilometers per second. That figure matters because it isn't only about speed, it's a clue to age. The faster an interstellar visitor is moving relative to its surroundings when it enters our system, the longer it's likely been wandering through interstellar space since being flung out from wherever it was born. And 58 km/s is fast enough that when University of Michigan researchers ran the kinematic math, they estimated a formation age somewhere between 3 and 11 billion years. An estimate later pushed toward 10 to 12 billion years by more recent isotopic readings from James Webb. Our own sun is 4.6 billion years old. This object predates the star we orbit. But before getting into the chemistry that revealed all this, we need to cover what happened in September 2025. A 36-hour stretch when most of the world's top telescopes went dark at precisely the wrong time, and what China quietly did during that window that hasn't gotten nearly enough attention. 3I Atlas was moving faster than any comet tracked this closely before, meaning any gap in observation wasn't a minor annoyance. It meant data lost for good. In late September 2025, as the comet neared its closest approach to the sun, several of the planet's most powerful observatories all happened to go offline at once. Hubble was undergoing gyroscope realignment to keep its pointing steady to within a tenth of an arc second. James Webb was switching instruments, a thermal stabilization process taking more than 24 hours. The Very Large Telescope in Chile was in the middle of cleaning its primary mirror using carbon dioxide snow jets to clear off microscopic dust. Gemini North in Hawaii and Gemini South in Chile had both shifted to other pre-scheduled programs. Planet hunting projects locked in months earlier through international time allocation committees that couldn't easily be reshuffled. And the result? A 36-hour stretch with no major Western optical or infrared telescope tracking 3I Atlas. In that window, the comet covered more than 1.2 million kilometers along its path. With no continuous observation, the record of its changing brightness as it heated approaching the sun had a gap right at the moment activity was expected to peak, a gap that introduced real uncertainty into models of how its ices were behaving, how quickly it was outgassing, what its rotation looked like, and what its dust-to-gas ratio was at peak solar heating. This wasn't trivial. It was a hole in the scientific record of the strangest object to pass through our solar system in memory. China filled that hole. High-altitude observatories in Tibet, Qinghai, and Yunnan don't run on the same maintenance schedules as Western facilities, and their day-night cycles and instrument calendars didn't overlap with the downtime affecting Hubble, the VLT, and the Gemini pair. The Ali Observatory in Tibet, the Qinghai Station near Delinga, and the Yunnan Astronomical Observatory stayed active through the entire blackout. At altitudes where thin, dry air cuts atmospheric interference dramatically, these sites kept their instruments trained on 3I Atlas, capturing its position, brightness, and the developing structure of its coma without interruption. Every observation carried a GPS-synced timestamp accurate to the millisecond. Every frame was archived in standard FITS format with complete metadata, transmitted to the National Astronomical Data Center in Beijing, checked for errors, run through calibration, and posted on the China VO Sky Survey portal within 12 hours of capture. There was no press release, no promotion, just a routine data update. But to any astronomer aware of what the Western network had just missed, those files were the single most valuable observations from that whole stretch. Once Hubble came back up, once Webb finished swapping instruments, once the VLT's mirrors were clean again, every research team's first move was pulling the Chinese data to recalibrate their work. Positional uncertainty for 3I Atlas fell from roughly plus or minus 25 arcseconds to under 5. The gap in the brightness curve was closed. The timing of peak outgassing was recovered. What had been at risk of going permanently uncharacterized now had full coverage. A 36-hour handoff from 3 mountaintop observatories in Asia had quietly become the foundation for every analysis that followed, with no announcement, no fanfare, just data uploaded and indispensable. This part of the story says something about how global science really functions. The world's largest telescopes cluster in a handful of locations, mostly across the Americas, mostly run by Western institutions, mostly booked through annual proposal cycles, set months ahead that can't easily bend for the unexpected. China's observatory network is built differently. Many mid-sized instruments running in parallel, automated scheduling flexible enough to pivot toward unfolding events, and geography that opens up different observing windows than Hawaii or Chile. For a fast-moving target needing uninterrupted coverage, that distributed setup proved more useful in a pinch than any single giant mirror. Now, here's where the story becomes genuinely hard to take in, because what all of these telescopes, Chinese, American, European, Japanese, measured together about 3I Atlas isn't just strange. It's the sort of finding that sends researchers back to re-examine assumptions treated as bedrock for decades. James Webb observed 3I Atlas in December 2025 as it moved away from the Sun following its closest approach in late October. Its ices, newly warmed by sunlight, were sublimating into gas, forming a bright coma of released molecules perfect for spectroscopy. Webb captured the chemical signature coming off the nucleus with a precision no earlier instrument could match. The results appeared in Nature on June 22, 2026. The first standout finding was the water, not ordinary water. 3I Atlas carries an extraordinary amount of heavy water, meaning water where one or both hydrogen atoms are replaced by deuterium, a hydrogen isotope with an extra neutron. Deuterium does exist in our solar system. Earth's oceans hold traces of it, and comets here contain small, measurable amounts too. Across our solar system's comets and oceans, the ratio of deuterium to ordinary hydrogen follows a pattern shaped by the conditions under which our solar system formed 4.6 billion years ago. 3I Atlas shattered that pattern entirely. Its water shows a deuterium to hydrogen ratio roughly 30 times higher than typical solar system comets, and more than 40 times higher than Earth's oceans. That's not a small anomaly or a slight deviation. It's a chemical makeup scientists have never observed anywhere in our solar system, and one that doesn't match any nearby star-forming region measured with current instruments either. Martin Cordner of NASA's Goddard Space Flight Center, who led one of the key spectroscopic studies, put it plainly, this is an object that doesn't match our own solar system or our own comets. And it doesn't match nearby protostars either, something genuinely new and different. Reaching that level of deuterium enrichment in water ice requires two things. First, extremely cold formation temperatures, since the chemistry that favors deuterium incorporation into water works best near absolute zero, far colder than the warm inner disk where planets form. Second, enormous amounts of time, since deuterium enrichment builds up gradually under extreme cold in dense molecular cloud chemistry. Together, these point to formation in the outer reaches of a very young galaxy, when molecular clouds were denser and colder than today, when the universe held fewer heavy elements, and when stars formed under conditions that no longer exist in our part of the galaxy. Webb's independent carbon isotope measurements told the same story. The chemical fingerprints of 3I Atlas place its birth somewhere between 10 and 12 billion years ago in a region of the galaxy far colder and more primitive than the cloud that eventually produced our sun. That's what China's study confirmed and built on. The unbroken coverage from Chinese observatories during the September blackout supplied the continuous brightness and position data that let ALMA, Webb, and other instruments confidently know exactly what they were observing at each stage of the comet's approach. Placing 3I Atlas's age at more than double Earth's age couldn't have been done with the same confidence without those gap-filling observations. The complete picture exists only because two parallel global astronomy systems were both running, and the one that drew the least attention ended up underpinning the result that mattered most. Take a moment with what this object actually is, because the figures are large enough to stop feeling real if you skim past them. 3I Atlas formed roughly 10 to 12 billion years ago, when the universe was under 4 billion years old. The earliest generations of stars had already lived and died, seeding the galaxy with heavy elements for the first time. Our sun didn't exist yet. The cloud of gas that would eventually collapse into our sun, our planets, and every living thing on Earth hadn't even come together. 3I Atlas was already moving through interstellar space through all of that. It was flung out of whatever star system produced it, likely due to a large planet passing too close, and it simply kept traveling. For billions of years, through the darkness between stars, through the Milky Way's spiral arms, through the frigid interstellar medium where almost nothing happens beyond the slow drift of ancient matter through ancient space. It was already ancient by the time Earth formed, having traveled longer than our entire solar system has existed before the first single-celled organism appeared in Earth's oceans. Then, after all that time, a trajectory set by a gravitational encounter more than 10 billion years ago carried it close enough to our sun to be briefly caught in our sky, spotted by a telescope in Chile on a Tuesday morning in July 2025, and studied closely by nearly every major observatory humanity has ever built. The ratio of carbon dioxide to water added yet another layer of oddity. In typical solar system comets, water dominates, and CO2 is a minor component, usually around a ratio of 0.12. In 3I Atlas, that ratio was 7.6, meaning over 60 times more CO2 relative to water than familiar comets show. That tells researchers the ices likely formed much closer to the CO2 snowline of their home star system, a far colder zone than where water ice forms, or that billions of years of galactic cosmic ray exposure heavily altered them during interstellar travel, or both. The carbon monoxide to water ratio was similarly extreme, near 1.65 versus the typical solar system value, around 0.3. We aimed Hubble, Webb, Spherex, ALMA, Gemini, the VLT, and more at this object, and together they tell a consistent story pointing one direction. 3I Atlas is measurably chemically unlike anything native to our solar system. It didn't come from nearby, and it didn't come from a star like ours. It came from conditions that existed early in the galaxy's history, conditions that no longer prevail anywhere near us, and it has carried those chemical signatures frozen in its ice for longer than our sun has been shining. There's also the question of what 3I Atlas did near Mars. Its path brought it within 0.1194 astronomical units of the planet on October 3rd, 2025. Not a collision, not even a close call by interstellar standards, but near enough that ESA's ExoMars Trace gas orbiter and another European spacecraft in Mars orbit both turned their instruments its way, capturing views of the comet's full coma structure from an angle no Earth-based telescope could match. Those images showed extended dust streams and complex outflow patterns consistent with vigorous, active sublimation from multiple spots on the nucleus's surface. Whatever was inside was escaping rapidly as solar heating intensified. So what does all this actually confirm about our worries? Not a threat. The comet never came within 170 million miles of Earth and posed no danger to anyone. What it confirms is something more philosophically weighty, and in some ways harder to sit with than a threat. The interstellar medium, the space between stars, isn't empty. It's populated by debris from star systems that formed billions of years ago and have long since burned out and cooled. These wandering objects aren't just rocks, they're archives, physical records of conditions that no longer exist anywhere we can observe directly. When 3I Atlas's ancient ices sublimated in our sun's heat and flooded its coma with molecules Webb could study, it released material frozen since before Earth existed, assembled under conditions current models of the early galaxy predict, but had never directly measured. In effect, we didn't just observe a comet, we sampled the early universe. And China's observatories made sure we didn't lose 36 hours of that sample during the most critical window for observing it. That's the practical truth beneath the dramatic headline. The broader implication for global astronomy isn't a comfortable one, but it deserves stating plainly. The story of the September blackout and China's role in covering it exposes a structural weakness in how humanity watches the sky. The largest, most capable instruments sit in a small geographic footprint, booked months ahead through funding systems that don't flex easily for genuine surprises. When they go dark simultaneously, even briefly, there's no Western backup. The assumption that the biggest telescopes will always be available is exactly the assumption that fails when it matters most. What China showed is that a distributed network of mid-sized instruments built for duty cycle, rather than raw depth, automated for quick repointing and spread across different night windows, can offer something the giant concentrated instruments can't: unbroken continuity. For a fast-moving, once-in-a-generation object like 3I Atlas, that continuity mattered more than any single observation from the most powerful telescope on the planet. The last point worth holding on to is what researchers said when the Nature paper published in June 2026. The isotopic fingerprint of 3I Atlas isn't just odd. It's unlike anything ever measured in our solar system or anywhere nearby. This object arrived from somewhere our instruments have never reached, from a time our telescopes can't access directly, carrying its chemistry across more than 10 billion years of interstellar travel, before releasing it briefly and brilliantly into the coma that glowed as it passed our sun. Researchers working backward from that chemistry, trying to pin down what kind of molecular cloud, what kind of early galaxy environment, what conditions could yield such extreme deuterium levels and such unusual carbon signatures, are still at it. No existing model fits the data perfectly. The object doesn't match anything in our current catalog of measured environments. That's what the new study confirmed. Not just that 3I Atlas is old, and not just that it's foreign, but that it genuinely, measurably falls outside every reference point we've used until now. The universe is older and stranger than our models assumed. The interstellar medium holds objects formed under conditions we've only theorized about. And the solar system isn't a sealed garden. It's a place things pass through, objects born before Earth or the Sun existed, shaped by an early universe that no longer exists anywhere close enough for us to study directly, except when one of them drifts through our sky, except when a survey telescope in Chile catches a moving speck and the numbers come back too extreme to be local, except when instruments from Hawaii to Tibet to Mars orbit all turn together towards something that, by last decade's science, shouldn't be here. 3I Atlas is already gone, past Jupiter's orbit, heading out of the solar system on a path that will never return. The ice it still holds will refreeze in the darkness of interstellar space. Its coma will collapse, its tail will fade, and it will keep drifting for another 10 billion years or more, carrying its ancient chemistry toward whatever lies ahead in the galaxy. But the data it left behind now lives in the journals, the archives, the spectrographs, the isotope measurements from James Webb and ALMA, anchored by the uninterrupted photometric record kept through a 36-hour blackout by observatories on Chinese mountaintops that almost no one had heard of before July 2025. The universe sent us a message frozen in ice 10 billion years old. We very nearly missed part of it. We didn't. Leave your thoughts in the comments. What does it mean that the oldest object ever observed in our solar system came from conditions no existing model fully explains? Subscribe, because the next video picks up exactly where 3I Atlas went after Mars, and shows what the data looks like once its full trajectory is mapped against the galaxy's history. Something visited us from the early universe. We studied it, and what it revealed confirms that the universe is older, stranger, and far more filled with ancient wandering debris than anything we feared or hoped.